Hello Internet, welcome to another tutorial in digital communication systems. In today's tutorial we'll talk about eye diagram. Eye diagram is an important aspect in analyzing a signal received as pulses. Eye diagram will tell us about the signal quality. It tells us about the state of the channel, and it is a visual examination of ISI, which is intersymbol interference. So if we were to note down the key points for an eye diagram, it'll be significance. We need to understand ISI first. ISI stands for inter-symbol interference, and the first key point about ISI is that it is not a noise. So it is not a noise, it is a phenomena by which the symbols tend to interfere with each other, and this happens because of spreading or a phenomena known as dispersion. And why does spreading or dispersion occurs? It is because of the non-ideal channel characteristics. So we need to understand that the characteristics of the channel are not distortionless over the entire bandwidth. If we are sending a pulse like this at the transmitter, it will eventually widen itself and be received like this at the receiver. And if two consecutive pulses are being sent, they are going to overlap with each other. And this, by the way, this phenomena is ISI, and you can see that this is there because of the dispersion. Dispersion, as you know, is the spreading of ISI, is going to affect the response of zeros and ones, and this eye diagram is going to be the resultant of all zeros and ones which are transmitted over a single bit period. So it is generated by overlaying the plots of received signal for every symbol time. So this could be termed as the definition of eye diagram. It is generated by overlaying plots of received signal for every symbol time. Now, in order to understand that, we need to take up a signal. For example, we have taken up a bit stream 110101, and in polar non-return to 0, it will look something like this. And I'm talking about the ideal wave shape for a code sent over few bits. Now, the eye diagram, which is the visual examination of these pulses received, can be seen on an oscilloscope. So on the screen of the oscilloscope, a bit time of TB is set for monitoring the pulses. So everything which is going to be monitored will be monitored within the width of this time period TB, which is, by the way, the time period of one pulse here. So we are going to plot the pulses in this box on the oscilloscope. Now when a 1 is received, it is plotted something like this. On the entire TB, it is plotted on the upper side of this reference line, which is known as the zero crossing. When the next one comes, it again overlaps on this, and when a 0 comes, it occupies this portion, thereby generating a visual like this. The next one will go here, the next 0 will go here, and the next one will go here. But as you can see, the ones and zeros will result in a square or a rectangular box to be formed depending upon the bit period. Now this is the case for an ideal waveform with polar non-return to zero coding. Let us take up the case of polar return to zero. A polar return to zero will look something like this. In polar return to zero, the 1 stays at a higher voltage for half the bit period time, and then it returns to 0, and the 0 stays at negative voltage for half the bit period time and then returns to 0. By the way, all the coding techniques are discussed in a separate video in greater details, but the fact of the matter is, if you draw the PDF, which is the power density spectrum of this polar return to zero waveform, it will be something like this, because only for half the bit time the power will be there. And if we plot the eye diagram for such wave shapes, which is still an ideal case, for 1 it will be plotted like this, and for 0 it will be plotted like this, but it will represent an eye. It is a representative of an eye, and that is why it is known as an eye diagram. And the opening of the eye, which is this distance, shows how much ISI is there, how much intersymbol interference is there. Now in this case the eye is fully opened, because a 1 on the pulse will take you to the maximum amplitude of the 1 at this interval, which is known as the best sampling instant. Now this is a perfect case of an eye where this distance in the center represents the best sampling instant. However, when dispersion or all kinds of distortions start to occur in the waveform, then the waveform would shift and would look something like this. So all kind of things are happening. Some waves are shifted over the period of TB. Some waves are spreaded, some waves have been lost in amplitudes, and so on and so forth. So if we look at the eye diagram for such waves, which is again plotted on the oscilloscope for the time period TB, it will look differently. So for the first one it will be something like this, for the second one it will be something like this, for zeros it will be this and this, and the next one would give me this. Now as you can see, the maximum eye opening, which could be represented by this distance, has lowered itself in value. So this distance has decreased, resulting in the closing of eye. So higher the opening, lower is the ISI, and the exact diagram that you would see in the books for eye pattern or eye diagram would look something like this. It is known as the distortion, and this center line is, by the way, known as the decision floor or the zero crossing, and this distance is known as distortion of timing. And this distance is the margin over noise. And this angle, by the way, is the slope, which decides the sensitivity of the timing. So we need this slope to be as high as possible, because a higher slope will result in higher opening of the eye, and a wide opened eye would represent lesser intersymbol interference. And this instant, and this vertical line right in the center, will be the best sampling instant, because a sample collected at such instant would tell you whether it's a 0 or a 1. So all in all, the eye diagram will tell us about the condition of the signal. It is the visual examination of ISI, which is a result of dispersion. Now dispersion itself is a topic that needs to be understood in a greater detail, because it is caused due to the changes in the amplitude response and in the phase response of the circuit, which results in fading and band limited signals that causes aliasing. So I hope the eye diagram and its significance and the key terms related to it are understood through this tutorial. And if you like the video, give it a thumbs up, and I'll see you in the next video. Take care. Bye bye.